Hi, my name is Christoph Saulder. I'm currently a postdoc at the Korea Astronomy and Space Science Institute, and today I will talk to you about BAO peak measurements using photometric survey data. Over the course of this talk, I will explain how we get to this plot here, what it means, and how we can get some useful scientific results from it. Of course, I have not been doing this research alone. I've been mainly working on this project with Srivatsan, who moved to the industry about half a year ago and from whom I have inherited this project. I'm also collaborating with my supervisor Yong-Song Song, as well as Jie Ding, Feng Shi, Ronpu Zhu, Ashley Ross, Jeffrey Newman and Albert Chuang on this research project. Let's start by reminding everyone of the basics. The baryonic acoustic oscillations, short BAO, are the imprint of the maximum distance acoustic waves could travel before recombination. As you can see in this animation, we start with some primordial overdensity in which the photon baryon plasma is forced into. However, the photon pressure will cause fast acoustic waves to propagate outwards. This, of course, is not happening in only one overdensity, but all of them. At recombination, the pressure drops and essentially freezes the pattern of the density distribution of the baryons. This will impact where galaxies will form, and we can detect this feature in an increase in number density at a certain distance. The distance scale imprinted in the BAO can be used as a standard ruler, which allows us to measure the expansion history of the universe and thereby constrain cosmological parameters. Now the main question is how to detect and measure BAO. For this example, we will pretend that I am the observer. Please ignore what is written on the door of my office. Okay, so I'm the observer in this scenario and I spot a galaxy just like this one over there. We can measure the redshift to this galaxy and use it to calculate the distance between me and the galaxy. And we will ignore peculiar motions and measurement uncertainties for now. If we look around a little bit more, we might spot another galaxy, like the one that just appeared over there out of nowhere. We can do the same measurements for the other galaxy as well, and then use the angular separation on the sky to calculate the physical separation between the two galaxies. We repeat this procedure for all galaxies in a very large sample and measure distances between each and all of them. By doing so, we can obtain the two-point correlation function.
In the simplest way, we get the two-point correlation function by simply measuring the distance between all possible pairs of galaxies and adding them up in a histogram, and then normalize the distribution by using a random catalog covering the same volume. This would be the natural estimator. However, it was demonstrated in Baryon 2015 and Sridhar 2017 that the DESI estimator is more robust, especially with more complex boundary conditions like a survey footprint with lots of masks for stars and other foreground sources, like our sample. This DESI estimator, short LS estimator, takes advantage of the cost correlation between the data catalog and the random catalog, in addition to the autocorrelation of the data and random catalogs respectively.
In an ideal world, we would know the physical distances to all galaxies like in this simulation. However, in practice we can only measure redshifts. The redshifts are not directly distances to galaxies, but are also affected by peculiar velocities, or as they are known in this context, redshift-based distortions. This makes life a little bit harder for us, but still manageable. However, DESI has just started measuring them and it will take several years for the survey to be completed. In the meantime, we can only use our dataset of photometric redshifts, which makes things much harder. This animation illustrates how photoset uncertainty washes out formerly clearly visible features. Sigma 0 is around 0.027 for our sample. In order to find a way to still recover BAO, you could either read up on this paper, or if you're a bit lazy just like me, we can simply turn to our previous loops of galaxies and I will illustrate the method for you. Good. Our two galaxies are still here. The vector connecting them can be separated into a transverse component sigma and a radial component pi. We call this ratio between the radial component and the separation S mu. Instead of measuring the correlation function just in fertile shells, as usual, we additionally split them into wedges corresponding to intervals in mu. The error caused by the large uncertainties of photometric redshifts will mostly affect the higher mu bins which are along our line of sight. However, the lower mu bins, which are orthogonal to the line of sight, are the least contaminated by photoset uncertainties.
This translates to the correlation function in the following way. On the x-axis we have the separation S, and on the y-axis we have the two-point correlation function as expressed by the LS estimator. First, to improve the readability of the plot, we multiply the y-axis by the separation squared. We can clearly see the BAO peak here. When comparing different mu bins of the same redshift error, we see that in the lower mu bins the BAO peak still remains detectable, while in the higher mu bins it gets notably washed out. At this point I want to give credit to the code that we are using to obtain the wedge two-point correlation function. FCFC is a fast Fortran based public code available here.
While we can spot the BAO feature in the data by just eyeballing it, we need a more profound way to measure the peak location. To this end, we will fit this function, which is based on Sanchez 2011. It consists of two terms: a power law gamma with a scale length S0 and an offset b, which represents the slope of the two-point correlation function. The other term, which represents the BAO feature, is a Gaussian with an amplitude n, with sigma 0 and a central location Sm. The BAO peak location is the aforementioned Sm.
In order to do a solid fit to our data points and to take into account the correlation between the different mu and S bins, we calculated a covariance matrix using MOX. We perform our maximum likelihood fit using this equation. Now, with most of our tools in place, let's have a look at some real data. DESI is a spectroscopic redshift survey that has begun its 5-year main observation run just about 2 months ago. It will eventually cover up to 14,000 square degrees of the sky. However, before one can run a spectroscopic survey, one needs to know where one has to point the fiber. To this end, the DESI Legacy Imaging Survey has been carried out to obtain photometric data for the DESI spectroscopic footprint and beyond. The data was collected using 3 different telescopes. The observation on the northern part of the survey, which were north of a declination of 32 degrees, were carried out as the Beijing Arizona Sky Survey using the BOC telescope for the G and R band, which was supplemented by the Mayal Z-band Legacy Survey. For the sky further south, the dark energy camera on the Blanco 4-meter telescope was used for a dark energy camera legacy survey, which includes the well-known dark energy survey. The latest release of the DESI Legacy Imaging Survey is DR9, which had notable improvements over the previous releases, especially in more crowded areas. It provides us with imaging data in the G, R and Z band, photometric model fits for all identified sources, matched infrared photometry from WISE, and most importantly, photometric redshift for all of them.
Within this vast dataset, we identify luminous red galaxies using the same selection criteria as the main DESI survey. but with additional masks to remove problematic sources near bright stars. We treat the data for the north and the south separately, as it was collected by different telescopes and has slightly different systematics. We also restrict ourselves to the spectroscopic footprint of DESI. Within this area we find about 5.8 million LRGs in the south and about 2.6 million LRGs in the north. We found that the optimal range for analysis is between a photometric redshift of 0.6 and 0.8, which is the best compromise between sample size and redshift uncertainty. Within this range we find 1.8 million LRGs in the south and about 800,000 LRGs in the north.
Now that we have a solid sample of observational data, we still need a matching random catalog for it. Luckily, the DESI Legacy Imaging Survey provides us with such a random catalog that even allows us to set the same masks as we did for the observational data. We only had to populate this random catalog with the correct redshift distributions. For the LS estimator, the random catalogs should have a higher density than the data catalog to avoid shot noise issues. We have settled on a 5 times higher density for the random.
Using all the tools and data I have explained before, we can finally calculate the Wedge 2-point correlation function for the LRGs of the DESI Legacy Imaging Survey DR9. We use 6 equally sized mu-bins and an S-bin width of 10/h megaparsec. Here we show our measurements for the lower 2 mu-bins in the south and here in the north. However, no measurement comes without error bars. In order to obtain these error bars, we use the covariance matrix that we will also use for our fit. The covariance matrix itself was calculated using 100 EasyMogs that were generated for DESI, whose 2-point correlation functions I'm displaying now. Oops! They are systematically offset from our measured correlation function. Well, this is because the EasyMogs were based on DR8 LRG target selection. The DR9 target selection has evolved considerably from it, mainly by relying more strongly on the Weiss magnitudes. As a side effect of this, the galaxy bias shifted and also the mean quality of the photometric redshift changed slightly. However, we can easily adjust these EasyMogs for the effects by multiplying their correlation function with a constant factor. Now everything matches fine, and we can fit the BAO feature to the data. You also might remember this plot over here from the beginning of my talk. The fit allows us to measure the BAO peak location by running an MCMC sampler. We obtain the following values. For the first mu-bin in the north we get around 97 megaparsec/h, for the second one 102 megaparsec/h, and in the south we measure an SM in the first mu-bin of about 101 megaparsec/h and in the second mu-bin of roughly 96 megaparsec/h.
So now we have the BAO peak locations measured for the LRG of the DESI Legacy Imaging Survey in the north for the first time, and in the south we have updated the already measured values that were obtained for DR8 by Sobersan and earlier work with the new DR9 data. But we want to get some scientific results from this. There is only one more step to go. We had to generate theoretical templates using the TNS model based on Planck cosmology. These templates depend on 5 parameters. The cosmic distance is dA and 1 by h, the GB normalized density function, the G theta coherent motion growth function, and the sigma p, the one-dimensional velocity dispersion. Luckily, as shown in Sridhar and Song 2019, the location of the BAO peak SM is only sensitive to the first 2 of them, which makes scanning the parameter space of the model much simpler. Using these templates, we jointly fit the peak location in each footprint and measure the alpha parameters, which in turn allows to get the angular diameter distances at the mean redshift of our sample, which is about 0.7 for a given fiducial cosmology. We get a dA of 1461 plus minus 110 in the south and a dA of 1400 plus minus 30 in the north. So, there are a few things that one might have already spotted. First, there seems to be a mild tension between the results of the north and the south. Moreover, the error bar in the north is much smaller than in the south, although the footprint of the south covers twice the area. Additionally, one might have noticed that the alpha value obtained from the data in the north indicated a significant offset from the fiducial cosmology. We want to remark that most of this seems to be caused by this very high data point in the lowest mu bin of the north data. As these are preliminary results, we are still working hard to understand the issues behind it. Another oddity that is not that apparent in the data presented here, but might be related to the issue, is that by comparing the photometric redshifts to the training set, the north should have a lower error than the south within our redshift range. However, measurements from clustering indicate that this is either not the case, or that there is a notable difference in the galaxy bias between the north and the south, which seems to be in conflict with other preliminary DESI data. As we are investigating this at the moment, it might be possible that we have already some answers during the discussion session. In summary, we have shown that the Wedge 2-point correlation function can be used efficiently to find the BAO peak location. We use data from the DESI Legacy Imaging Survey to measure the BAO peak location of an LRG sample around the redshift of 0.7 in two distinct footprints on the sky. We used our measurements to infer the cosmic distance dA using model templates. While the results for the south agree with previous measurements, our results for the north are still problematic and we are still trying to understand the issues and systematics behind it. And please keep an eye out for our forthcoming paper, which will be hopefully submitted soon and which will contain a clear answer to the remaining issues.
Thank you, and I'm looking forward to answer all your questions either during the live discussions or any time in the dedicated Slack channel.